Pleasant morning to one and all. I'm Dr. Sumitra, an associate professor from the Department of Computer Science and Engineering. And today we are going to discuss about the nested accelerated gradient descent from the neural network. In a realm of deep learning, optimizing the training process is paramount to achieving the accurate model effectively. Gradient descent is a fundamental optimization algorithm used to minimize the loss function during the training of a neural network. However, the traditional gradient descent has its limitation, especially in the presence of noisy gradient and oscillation. This is where the techniques like a gradient descent with the momentum and the nested accelerator gradient descent comes into play, offering the improvement and refinement to the optimization process. A gradient descent is a first order optimization algorithm used to minimize the loss function by iteratively moving in a direction of a speedy ascent of the loss. The basic idea is to update the model parameter in proportion to the negative of the gradient to the loss function with respect to those parameters. Mathematically, the update rules for the gradient descent can be represented as theta t plus 1 is equal to theta t minus alpha delta of t L of theta t, where this theta t is a parameter vector at an iteration of theta t1, and alpha is a learning rate and the delta of L of theta t is a gradient of the loss function with respect to the parameters. The main drawback of the gradient descent of the traditional gradient descent, while the gradient descent is effective in many causes, it suffers from the certain limitations like a slope convergence. In a deep learning where the loss surface can be highly non-convex, traditional gradient descents can coverly slowly, and oscillations where the loss surface has narrow and illuminated value gradient descents may oscillate around the minimum. A noisy gradient, in practice, a gradient computed from mini batches can be noisy, leading to the accurate updates and the lower convergence. The gradient descents with the momentum. The gradient descent momentum is optimization with the traditional gradient descent that addresses some of its drawback. The key idea behind the momentum is to add the fractions to the updated vector of the past time steps to current the update. This helps in smoothing out the occasional oscillation and accurate convergence. The updated rules for the gradient descents with the momentum is given by V of t plus 1 is equal to delta of t, Vt plus delta of L of t, where theta of t plus 1 is equal to theta of t minus v of t plus 1, where v1 is the velocity or the momentum of the iteration t, and we have a momentum terms typically between 0 and 1. Alpha is a learning rate and delta of t L of theta t is a gradient of the loss function, where the Nestors accelerated gradient is also known as Nestors momentum, built upon the idea of a momentum introduced in a gradient descent with a momentum. It was proposed in 1983 and has become a popular optimization algorithm due to its faster convergence and ability to handle a noisy gradient. The key difference between NAG and the traditional momentum lies in when the gradient is computed. Instead of computing the gradient at the current position of the parameter, NAG computes a gradient at a slightly look-ahead position. This look-ahead position helps in making a more informed updates, reducing the life hold of overshooting the minimum. The updates a rule for the Nestors accelerator gradient descent where V of t plus 1 is equal to alpha of V of t plus alpha delta of t theta minus 1. Vt is a velocity or a momentum at the iterations, and V is a momentum term. Alpha is a learning rate. Hence, we can also conclude by stating it's the optimization algorithm plays a crucial role in a deep learning traditional gradient descent, serving as a foundation, and its limitations has a low convergency and susceptibility to the oscillation. The gradient descent with the momentum and accelerated gradient descents offers enhancement to address these issues. Hence, a gradient descents with the momentum introduce a momentum term that smoothen out the oscillation and speed up the convergence. The nectar accelerator gradient steps further by computing the gradient and the locate position. I hope you're clear with this concept. Thank you.